Now, to the extent that the actual velocity during the interval doesn't deviate much from the straight line approximation, and in most real-world situations there is some deviation between the actual evolution of the velocity here and the straight line approximation. But to the extent that that deviation is not very significant, then we can say that v bar will occur at the midpoint of the interval, as we've seen here, and that v bar is going to be halfway between v naught and vf. Of course, v naught plus vf over 2 is halfway between v naught and vf. And we can think of the average velocities being the average of the initial and final velocities, again for the straight line approximation. And also, to the extent that we don't deviate much from the straight line velocity versus clock time graph, the acceleration is constant, so we can write the average acceleration is equal to the acceleration which is constant. So the acceleration is constant everywhere on the interval. Again, this is the case to the extent that the actual velocity doesn't deviate much from the straight line, and we could quantify that, we could analyze that, but right now we'll leave that as kind of an intuitive idea. Okay, now, you notice that this graph forms a trapezoid. The sides here are parallel, and the base, or what we're going to call the base, actually in correct geometric terminology, these two are the bases. The bases are parallel, and an altitude runs between the two bases. On the graph, we're going to consider this, which is actually an altitude, to be the base, because it looks like the base of this figure. And these two distances to be the altitudes. So we distinguish this by saying that this is a graph trapezoid, and for graph trapezoids, this thing that's actually geometrically an altitude is the base, and these two bases are what we're going to call altitudes. Now, we see that we get a figure with an altitude here, and a base here. What we want to do is we want to consider the area of this trapezoid, and you should know by now why we want to do that, because the area is going to turn out to represent the difference in position or the displacement on the interval. Okay, to make a trapezoid into an equal area rectangle, because we know how to find the area of a rectangle, there's a formula for the area of a trapezoid, but it's kind of very useful to understand how we can derive that area and use it to think about the graph trapezoid. So, we take the graph trapezoid, we have a midpoint of the segment that represents the velocity versus time, and we have a dotted line here that represents the midpoint altitude of this trapezoid. So here's our midpoint altitude from here up to here. Notice I've got this line extended all the way across. Okay, what we're going to do is we're going to cut the trapezoid right here. We're going to cut out this little triangle. And then we're going to lift that triangle up, separate it from the rest of the trapezoid. And then we're going to simply take that little triangle and flip it around, put it here. Now, it's almost a trivial geometric exercise to show that the triangle you need here is congruent to the triangle that we cut out here. I'm not going to go into that much detail. That's something you should think through, because you really do need some geometric reasoning for many parts of this course. Okay, in any case, we've constructed a rectangle whose area has to be equal to that of the original trapezoid. Now, what's the dimensions of this rectangle? Well, the altitude is the midpoint altitude of the original trapezoid, and the width is the original width. So the area is simply the midpoint altitude multiplied by the original width. Now, what's the point of this? Well, the point is simply that the trapezoid we're talking about from our original picture has altitudes V0 and VF. Midpoint altitude is going to stand for V bar, because altitudes on this graph stand for velocities. So at the midpoint we get the average velocity V bar. When we rearrange the rectangle, we have a rectangle whose altitude is V bar, whose width is delta t, whose area is therefore V bar delta t. Now the question is, what does V bar delta t mean? Well, we go back to the definition of rate of change. Now you might know perfectly well what V bar delta t is, but if you can't connect it to the definition of rate of change, I'm going to assert that it's important to be able to do that. So, since V bar equals ... change in A over change in B and all that stuff, it's the rate of change of position with respect to clock time. And the change in position is delta x, change in clock time is delta t. And from this fact that V bar equals delta x over delta t, we conclude that delta x equals V bar delta t. And that's the change in position. I'm sorry, my writing's kind of bunching up here a little bit, but delta x is your change in position, which we call the displacement. I'm not sure if I was standing in front of the camera there. I probably was when I wrote that. But here's our conclusion, that the area of the trapezoid is equal to the change in the position. So we conclude with the statement that a V versus T trapezoid is characterized by the fact that the slope is the average acceleration corresponding to the interval represented by the trapezoid. The area is the approximate change in position. Now, if the trapezoid is exact, if it exactly represents the motion of the object, meaning that the velocity evolves in a perfectly linear fashion, then you can drop the word approximate here. And the change in position is the displacement.